Good day and welcome back to the second part of our discussion on differentiation formulas. And as a reminder from our previous discussion, the differentiation formulas in a sense will give us some shortcut formulas that can be applied so that we will not always have to go back to the kind of longer, more tedious definition of the derivative. What we saw in the previous examples is that the derivative of a constant is always going to be equal to 0. And then we saw the power rule. And the power rule tells us when we're differentiating x raised to the nth power, what we will get back is nx to the n minus 1. That is to say the power n comes down front. The new power is 1 less than previous. In this video, we will explore 2 additional properties and set the stage for what is to come. The first of which is the constant multiple rule. If c is any constant whatsoever, and f is a function that we can differentiate, then the constant c can simply be pulled in front of the derivative. That is, this is c times the derivative of f of x. So let's go ahead and maybe give a short explanation as to why we would expect this to be true. So if we wanted to take the derivative of c times f of x, what we could do is let g of x be a constant times f of x, and we could calculate g prime of x. And hopefully what we would get back is c times f prime. And this is just a reminder that all of these differentiation formulas that we are going to introduce and discuss, we could get these by going back to the limit definition of the derivative. So I want to, just for one more example, go through that explanation, but this will be the last time, I promise. So in this case, by the definition of the derivative, we have the limit as h approaches 0 of g of x plus h minus g of x all over h. And note, we are substituting in x plus h to our function. So this would be the limit as h approaches 0 of c of f of x plus h minus c times f of x all divided by h. And note, we have a constant c in each term, and we can not only factor a c out of the top, but we could go ahead and pull the c out in front of the limit. And when we do that, we are left over with the limit as h approaches 0 of the familiar difference quotient, f of x plus h minus f of x over h. That is, this is really equal to c times f prime of x. And we have verified that this desired constant multiply rule is in fact true. We also have what we might think of as a sum difference rule. And for now, the differentiation formulas are working out in a very similar fashion to the limit laws, and they're matching up with our intuition. We can pull out constants, and it turns out that you can also break up the derivative over a sum, and you just as easily could break it up over a difference. That is, the derivative of f plus g is the derivative of f plus the derivative of g, and vice versa, the derivative of f minus g is the derivative of f minus the derivative of g. And note, this was the rule we actually utilized at the end of the previous video. With all of this in place, we can now differentiate any polynomial function by applying a combination of these 4 formulas. So just an arbitrary example. If we would like to differentiate this, the sum difference rule tells us we can break it up into 3 separate derivatives. And we could write this as the derivative of 3x to the 17th plus the derivative of 2x squared minus the derivative of 7. And then working our way from left to right, we know in the first two a constant can be pulled in front of the derivative. So this would be 3 derivatives of x to the 17th plus 2 times the derivative of x squared, and the derivative of a constant is always 0. And now we can go ahead and apply the power rule. So in this first derivative, we have the power rule with n equals 17. So that 17 comes down front, and the new power is 16, so 1 less than 17. In the second term, note we have a function which we've already differentiated, x squared, but in this case we're using the power rule with n equals 2. So the 2 comes down front, and the new power is 1 less. So exactly as we saw in our previous video. And that leaves us with 51x to the 16th plus 4 times x to the first. Now, note in this first kind of encounter of differentiating a polynomial using our differentiation formulas, I have shown all of the details or steps. It certainly would be okay if you were to just jump right down to this third step, and in fact, that will be the preferred thing once we've worked through several examples and we have a better understanding. So in terms of what we've seen now, we can differentiate x to a power, we can pull constants out of derivatives, and we can also break a derivative up over a sum or a difference. And the natural question that hopefully leaves you with is, what about products, or what about quotients? And that will be the topic for our next video discussion. So stay tuned and take care.